Swayam Prabha. Digital India. Educated India.
Hello friends, so welcome to the course Introduction to Sampling Theory. So you can recall that in the last lecture we had considered the concept of ordered estimator, that when we are trying to draw the sample observations from the population, then it matters that which of the sampling unit has arrived in my sample at which order, first draw, second draw, third draw, or say nth draw. And based on that we had constructed the Deshraj estimator, which can give us an unbiased estimator of the population mean when we want to use the PPS WOR. That means probability proportional to size without replacement. So now the question is this: now we know that how to construct an estimator based on the ordered observations, or how to use the information on the order of the observation. So when there can exist an ordered estimate, why not there can exist an unordered estimator also? And you see that there is a relationship between the ordered estimators and unordered estimator in terms of their number and their probabilities of collection, right. So this is the topic of the lecture today, that we are going to consider here unordered estimators, but before that we will try to develop some general results, that what is the relationship between the total number of ordered and unordered samples for a given sample, and what is the relationship between their probabilities of selections, and based on that we will try to develop an estimator based on this unordered samples, right. So let us begin our lecture, and if you want to download the slides of this lecture, you can go to my home page, and from there you can download these slides in the PDF format, and the address where I have uploaded these slides is home.iitkc.ac.in/SHALAB/SP, and if you are facing any problem in reaching to this address, you can also scan this QR code and using any free application on your phone, and you will come to this address. And still, if you are facing any problem, you can go to any search engine on the internet, and you can type my name and my institution name, IIT Kanpur, and hopefully you will arrive at my home page. From there you can download the slides. Okay, one thing before I begin in this lecture, you may see that at some places the expressions may be little bit longer. They are not really longer if you try to write down in your copy, but when I am trying to do it on my slides, yeah, I have to make it bigger so that I can explain you easily. So don't get horrified with those expressions. Number one, they are extremely simple, and I always say lengthy does not mean complicated. They are not complicated at all, that's my promise to you. But unless and until you try to write them on your own copy with your own hand, with your own pen, you will not understand them. You can understand them from the slides, but you will not get a feeling, you will not get a confidence unless and until you do them yourself. So that is my first request to all of you, that whatever we are going to learn in this lecture, please try to surely do all the algebra, at least try to write those expressions with your own hand, and that will help you, right. So now we are going to talk about unordered estimator. So when we consider the ordered estimator, the order in which the units are drawn was considered. And corresponding to any ordered estimator, there exists an unordered estimator which does not depend on the order in which the units are drawn and which may have a smaller variance than the ordered estimator. Don't you think that this news is a pretty good news? That you are facing so many issues in the case of this ordered estimator, but still you conquered all of them. Now you are saying that using any ordered estimator, you can also construct an estimator which has got even the smaller variance than the estimator which is based on the ordered sample? Yes, that's the reason we are in this lecture today. So that is what we are going to discuss. But before that, we have to understand what is really meaning by unordered and ordered estimator and how they are interconnected. Do you recall? Do you remember that in the case of simple random sampling, we have learned that when we are going to draw a sample of a small n size from the population of size capital N, then there were n choose n number of samples, right? So when you are trying to do it without a replacement, then possibly if you try to think once again, these were unordered samples of size n, right? You had not considered the order, right? Whether if you are trying to draw a sample of say y1, y2, y3, in which you are getting say in the first unit you are getting y5, in the second unit you are getting y10, and in the third unit you are getting the capital Y1 unit from the population, you could not bother whether this is y1, y2, y3 or the way in which these units are coming into the sample, or this is y2, y1, y3. You were not bothered about it. So there were n choose n unordered samples. Now I am telling you that corresponding to any unordered sample or samples of size small n units, there are factorial n number of ordered samples. You know the meaning of this factorial. For example, factorial 3 is 3 into 2 into 1, factorial 4 is 4 into 3 into 2 into 1, and factorial 4 is 4 into factorial 3 also, right? That you know. So now means I would like to illustrate this result with a sample of size 2 as an example. Suppose I try to choose a sample of size small n equal to 2, and suppose there are two units u1 and u2 which are chosen. Now you can create here two factorial 2 ordered samples. This is actually u1 u2 and u2 u1. So you can see that in the first case u1 is appearing, and in the second draw u2 is appearing, and in the second sample u2 is appearing in the first draw and u1 is appearing in the second draw. But in case if you don't consider the order of this sample, then these are simply u1 u2. So there is only one unordered sample. Now in case if you try to find out the probability of occurring of this unordered sample u1 u2, then this can be written as the sum of the probabilities of the sample u1 u2 plus the sum plus the probability of the sample u2 u1. So the probability of unordered sample is now expressed as the probability of ordered samples, right? So this is true for this sample size equal n equal to 2. Now I try to show you how will it hold for say sample of size 3. Means beyond that it will become difficult for me to write down all the combinations here, but it will true for in general for a sample of size n. So for small n equal to 3, there are 3 units, small u1, small u2 and small u3, and from there we can have factorial 3 which is equal to 3 into 2 which is 6. So there will be 6 ordered samples. What are those samples which I have written here? u1 u2 u3 u1 u3 u2 u2 u1 u3 u2 u3 u1 u3 u1 u2 u3 u2 u1. But in case if you try to ignore the order of the sample, then there is only one unordered sample which is u1 u2 u3, that's all. So now you can see here corresponding to one unordered sample of size 3, there are factorial 3 number of ordered samples. And in case if you want to compute the probability of observing the unordered sample U1, U2, U3, this is going to be probability of occurring of first ordered sample, occurring of second sample, probability of third sample, probability of fourth sample, probability of fifth sample, and probability of sixth sample, and this is what I have written here. Right. So, you can see here that the probability of an unordered sample is once again expressed as the sum of the probabilities of ordered samples. So, this is what we have to understand now here. Now, I try to formalize it, and I try to construct the estimators based on the ordered sample, and then we have to learn that how we are going to combine them so that we can obtain a good estimator based on that. So, let ZSI be an estimator of the population parameter some theta based on some ordered sample, say Si. So, now obviously here this smallest will go from here 1 to n choose n, and I will go from here 1 to factorial n. So, now let us try to write this m as factorial n, so that that will help us later on in making the thing simpler. So, now you can see here that you have ordered sample. For example, you have obtained 6 samples in the case of sample of size 3. So, you had S1, S2 up to here S6. So, this is what I mean by this capital SI. So, corresponding to that sample, you have created an estimator for the population parameter theta. Now, at this moment I am simply trying to take a general estimator. Later on this theta will be your population mean. Okay. So, now we are going to consider here a sampling scheme for choosing the samples in which the probability of selecting the ordered sample, say Si, is PSI. So, this PSI is the probability of selection of this capital Si. Now, we have understood that, for example, in the case of n equal to 2 and n equal to 3, I had shown you that the probability of an unordered sample can be expressed as the sum of the ordered sample. So, that is precisely the same thing I am trying to do here, and the probability of getting an unordered sample, this PS can be expressed as the sum of all the individual probabilities of the ordered sample, and capital M is here factorial n. That is why I had written here capital M, because it was not looking nice to write down again factorial n on the in the summation limits. Right. Now, if you try to see what are we going to do. Suppose we have a population of size capital N, and it has units, say here 1 to up to here capital N, and then we are trying to draw here the samples of size small n. So, small n's are what are going to be? They are going to be n tuples type of thing. For example, if you have 3 units here y1, y2, y3, then you can obtain here, say here y1, y3, y2, y3, y1, y2, and so on. So, what are these things? These are 3 tuples, right? This is another 3 tuple. So, now what will happen, that when you are trying to obtain the nth draw, then in the nth draw the sample space will consist of n into n minus 1 into n minus small n plus 1 number of unordered sample points. So, now I have to find out what is the probability of collection of any of this ordered sample. So, let me try to denote it by PSIO, means SI means SI is sample and O means here ordered sample. So, the probability of selection of any ordered sample will be 1 upon this number. So, this is 1 upon n to n into n minus 1 into n minus small n plus 1. And now, there are factorial n combination. So, the probability of selection of any unordered sample corresponding to this ordered sample will be the, say, factorial n times this probability, what you have obtained here, right. This will be added, say, capital M times, for example, probability of y1, y2, y3 plus probability of y3, y2, y1 plus probability of y3, y1, y2, and so on, all the 6 probabilities, factorial 3 probabilities. So, I can write down here this as say here factorial L n into probability of selection of any of the unordered sample, right. So now in general I can write down here Ps is equal to I goes from 1 to factorial n Ps IO, which is here factorial n into factorial n minus n upon capital N, which is nothing but 1 upon n choose n, right. So this is now we have obtained such a result. Now once we have learned how to obtain such probabilities, now I am going to define here an estimator which is based on unordered sample and which has a connection with the estimators of the ordered sample. And remember one thing, I am up to now in this theorem or in this result, I have taken a estimator theta. I have not talked about the capital Y bar. Well, Y bar will be equal to theta later on, but at this moment I am just trying to take here a general result. So suppose now you can see here what is happening, that we have got here different types of ordered sample. From each of the sample I can create an estimator under PPS or say varying probability scheme without replacement. Now we have different estimator. Now the question is, how are we going to combine it? We would like to combine it such that it gives us a nice result. So what we want, that the properties like unbiasedness, smaller variance, etc. have to be satisfied. So now the question is, how one can combine the estimators which are obtained from the ordered estimator in such a way such that the new estimator is an unbiased estimator of the parameter and it has a smaller variance than the ordered estimator. Because if the variance is not smaller, then there is no fun, there is no advantage. So now here we have a result, we have a theorem in which we are going to discuss that how the estimators of unordered samples are going to be combined. So let theta 0 hat be equal to ZSI, right. That means an estimator which is based on the ith sample, say here Si, which is obtained by PPS WOR or say varying probability scheme without replacement, but this is an ordered estimator. Now we are saying we are trying to define another estimator theta hat u. U means unordered, and this is going to be defined as the sum of this is I into P transpose Si, and summation is going from I goes from 1 to capital M. Capital M means factorial N. So now what are we trying to understand, that we have to use the ordered estimator and we have to find an estimator theta hat u which has a structure like this one, where this P transpose Si, this is here given by like this, right. This is PSI upon PS, and PSI is the probability of selection of the SIth ordered sample, and PS is here the sum of those probabilities. So if you try to construct such an estimator theta hat u using this philosophy, using this methodology, then both this ordered and unordered estimators are going to have the same expectation. So in case if theta hat 0 is unbiased, then theta hat u will also be unbiased, but the variance of this theta hat u will be less than or equal to the variance of theta hat 0, which is based on the ordered estimator. So now you can see here, this theorem is trying to give you a guideline that if you have got say different estimators based on different types of ordered sample, then how you can combine them such that you can have the same amount of biasness as of the ordered estimator. So, in case if the ordered estimator is unbiased, this new estimator will also remain unbiased, but the difference will come in their variances. The variance of the unordered estimator which you have obtained by this methodology will always have a smaller variance than the corresponding ordered estimator. And please remember this result, we are going to use it now. Right. So, what you have to keep in mind that how you are going to construct that theta hat u. In order to construct the theta hat u, you need PSI, you need PS and you need ZSI. These are the three ingredients that we have to keep in mind. But before try to use it, let me try to show you here the proof. The proof is extremely simple. So, first we try to show the unbiasedness part. So, the total number of ordered sample is going to be factorial n into n choose n. Now, in case if you try to take the expectation value of theta hat 0, this is going to be s going from 1 to n choose n and I goes from 1 to factorial n, which is here denoted by capital M, ZSI, PSI, because the probability of selection of the ith ordered sample is PSI. So, that will become ZSI, PSI. Now, in case if you try to consider the expected value of theta hat u, that is the unordered estimator, the same limits for the summation, double summation over SNI, ZSI, P prime SI. So, now you see this is here one thing and whole this things is occurring with the probability PS. So, now you have to simply you have written here that your P transpose SI is given by PSI upon PS. So, why do not you substitute this value over here, and once you try to substitute it here, this PS gets cancel out and then we have here double summation ZSI PSI. And what is the double summation ZSI PSI? That is the same thing, same as expected value of theta hat 0. So, you can see here that expected value of theta hat u and expected value of theta hat 0, they are the same. Okay. Now, I come to the part of variance. So, since we have taken theta hat 0 to be ZSI and which is occurring with probabilities PSI. So, obviously, in case if I try to consider here another random variable theta hat 0 square, which will become square SI, this will also occur with the same probability PSI, right. So, where I goes from 1 to m and s goes from 1 to n choose n. So, now I try to construct here two form theta hat 0 square and theta hat u square. So, similarly, the way you have decided for theta hat 0, you can also decide for theta hat u. Theta hat u is occurring with probability PS. So, theta hat u square, which is here like this, will also occur with probability PS, right. And this is obvious if you try to say here if x is following a f some PDF fx theta, then expected value of x is going to be here summation say here xi fxi theta, right. But if you want to find out an expected value of x square, then this is summation xi square f of xi theta, right. This PDF remains the probability mass function remain the same, right. And the same thing is true for the continuous random variable also, that expected value of x will be say here fx theta dx and expected value of x square will be integral x square fx theta dx, right. The PDF remains the same. So, that is the same thing here now. So, now we try to find out here the variance of theta hat 0 and variance of theta hat u. So, variance of theta hat 0 is given by expected value of theta hat 0 whole square and minus expected value of theta hat 0 and the square of this whole expectation. So now, as per the fundamental definition, this will become here z square psi, that means the value and its probability, and minus expected value of theta hat 0 square whole square. And similarly here, variance of theta hat u will become means expected value of theta hat u square, which is by definition this summation over s and summation over I z si p prime si whole square into its probability ps minus expected value of theta hat 0 square. Because if you try to see, I have shown you that that earlier that expected value of theta hat o and expected value of theta hat u, they are the same. So I am replacing it here. Okay, now you simply try to take their differences. So their difference will come out to be double summation carry square psi minus summation s, this summation whole square into ps. Now I try to do here one thing. Means if I have a term like summation x whole square, I can write down here as a summation x into summation x also. So that's what I'm trying to write down here. And in case if I have a term like minus times summation x whole square, so that can be written as summation x square minus twice of summation x whole square, and this summation x whole square can be replaced by say summation x whole square minus twice of summation x into summation x. Yeah, that will not make any difference, that is the clear cut algebra. So I try to write down here this quantity here like this summation minus twice of summation into summation. You can see here this square is now broken into here two parts. That is the same thing, that does not make any difference, but this will help us in the algebra. So now you can see here that I am trying to write down, I am trying to take out this summation over s outside the bracket, it is here, it is here, it is here. So now the remaining quantity is here, right. And now here you have psi, here you have psi, here you have psi transpose, and here you have here summation like this thing here, right. So now what I am trying to do here, I simply try to simplify it and I try to take this summation I outside. So this quantity comes here. Yeah, you have to do a very simple algebra here, nothing more than that, right. And you can see here, doesn't it look like something like x square plus y square minus twice of xy? So this I can write down here zsi minus summation zsi p transpose si whole square into psi. And now you can see here that this summation is always going to be greater than or equal to 0. This is always positive. So this difference which you are trying to obtain here, this is greater than 0, and hence the variance of theta hat unordered is always smaller than or equal to variance of theta hat ordered estimator, right. So if you try to see here, in this result we have shown that if you have got some ordered estimators, you can construct an unordered estimator which is going to have the same expectation. Both of them are ordered and unordered estimator, they are going to have the same expectation, but the variance of the unordered estimator is going to be smaller than the variance of the corresponding ordered estimator, right. You have to be a little bit careful with my pronunciation, because ordered and unordered, they appear to be the similar in voice sometime. So once again I will say variance of unordered estimator is less than or equal to variance of ordered estimator. So that means unordered estimator becomes more efficient. Okay, now in this result what you have to keep in mind, I have not assumed any particular parameter and I have not assumed any particular methodology also. I am saying that this estimator which is based on ordered sample can be constructed by any other approach, by any methodology, by any concept. What I need here is only the ordered estimators, and I am saying that I want to combine them using this methodology, using this formulation. And in case if I try to do it, the resulting estimator is going to have a smaller variance than the original estimator. Original means the one which is based on ordered sample. So now we have to understand one thing more, that what will happen to the estimate of this variance of this unordered estimator. So for that, what I can consider here, that variance of theta hat 0 minus variance of theta hat u is given by this quantity, right. So I can simply means just take the hat over these quantities. So the hat here. So now this one I can see here that this will become here summation over P transpose SI, estimate of variance of theta hat 0 minus this quantity. So this is one can actually find out the using this relationship, actually only one can find out an unbiased estimator of the unordered estimator, variance of the unordered estimator, that is based on the estimate of the variance of ordered estimator. So this is how one can find out here. Now using this result, now we try to use some methodology and try to obtain such an estimator, right, because now we have got a methodology to construct the unordered estimator using the unordered estimators, using the ordered estimator, and from this theorem we are clear, we are now confident that if we try to follow this approach, they are going to give us a smaller variance, they are going to give us smaller variance and they are going to be more efficient, but they will have the same bias as of the ordered estimator. So now we have here an estimator which is called as Murthy's unordered estimator, and this is based on the Deshraj ordered estimator. You see, up to now we have done only one methodology by which we can construct the ordered estimator, that is Deshraj estimator. So now what are we going to do? That we will try to implement the Deshraj estimator what we have developed, and using the philosophy of this theorem we are going to construct a new estimator that is going to be called as Murthy's estimator. And just for the sake of understanding, first we are going to consider the sample of size 2. We will try to develop the Murthy's estimator for a sample of size 2, and then I will try to extend it for a general case. So as you have seen in the case of Deshraj estimator, that it was easier for you to understand the concept algebra methodology when we have only 2 observations, or when we have to select only 2 observations from the population. So that is the same thing I am going to now do here. So now we consider the Murthy's unordered estimator corresponding to the Deshraj ordered estimator for a sample of size 2 only. So let this small yi and small yj be the values of the units capital Ui and capital Uj, which are selected in the first and second draws respectively. And whatever the values we have selected, small yi and yj, they have got the initial probabilities as small pi and small pj. They are the corresponding initial probabilities of the selection. We had discussed this thing earlier also. Right. So now we have got only here 2 units, yi and yj. So now there are 2 possible samples, yi comes first, then yj, or yj comes first, or say yi. So these are going to give me sample number 1 and sample number 2, which I am denoting here as a S1 star and S2 star. So in S1 star we select ui uj, so that we have here small yi small yj, and in second sample S2 star we are getting here uj ui, corresponding to which we have small yj yi. Right. Now we have to first construct the Deshraj estimator for both these samples, S1 star and S2 star. Right. So If you remember, the Deshraj estimator's form was given by like this. Now I try to consider this thing, this form to construct my ZSI, and I am denoting here as a Z bar S1 star. That means this is based on the first sample, and this is nothing but this was your Deshraj estimator, nothing more than that. Okay, look into your earlier notes. This is the same expression. I have simply just rewritten it in this form so that it is easier for us to write such a form when we are trying to consider the general structure. And similarly, when I try to replace here this yi by j and j by I, then I will have one more estimator which is based on yj yi, which is your here S2 star. So I simply have to replace here this thing, and I will get here this form, which is the Deshraj estimator when we are trying to consider yj yi. Right, and this is the same thing which I have written here. Okay, so you simply have to use that Deshraj estimator, and you simply have to use instead of y1 y2 you have to use yi yj, and then once again you have to use yj yi, and you will get this Z bar S1 star and Z bar S2 star. So now these two estimators, Z bar S1 star and Z bar S2 star, they are my two ordered estimators. Now what I will do, I have to combine them. So as we had discussed that in order to combine them, what we need here the probabilities of the collection of S1 star, and from there we have to find out the probability of S, so that we can construct the probabilities P prime S1 star and P prime S2 star. So now you already have done this thing in the case of Deshraj estimator. What was the probability of drawing yi yj and yj yi, right? So the probability of selection of the first sample S1 star corresponding to yi yj will become here pi pj upon 1 minus pi, and for the second sample you simply have to replace I and j, you have to interchange it. So this will give you the probability of selection of the second sample, which is yj yi. Now this PS was defined as the sum of these two probabilities, so I am summing in, and this is my expression. Now based on that we have defined the P prime S1 star as a PSI divided by sum of PSI. So now this will become here, this first probability will become here PS1 star divided by PS, and if you try to take the ratio of this quantity and this quantity, it will come out to be here like this, right. So this is your here P prime S1 star, and similarly you can find out here PS2 star divided by PS, and you will get here this thing. So essentially you have to simply replace or interchange I and j, nothing more than that. But I would request you that you please try to take paper and a pen and try to obtain these steps yourself. Okay, these are very simple steps. Now I try to use my theorem, and I try to find out here an unordered estimators which is based on the Deshraj ordered estimator. So I simply try to use the theorem where we have obtained theta hat u using theta hat 0. So I try to use here the same theorem. You can see here this estimator was defined here as say like this: theta hat u is equal to I goes from 1 to capital M, that is I P prime S I. So this is, there are factorial 2, means there are two terms. So this becomes here Z bar S1 star into its corresponding probability P prime S1 and Z bar S2 star P prime S2. Now you simply have to substitute here these two values which you have obtained here, P prime S1 star and P prime S2 star, and you can get here this expression. So this is your Murthy's unordered estimator corresponding to the Deshraj ordered estimator. Now before I go further, If I ask you, can you simplify it? What you have to do? You simply have to just substitute all these values which you have obtained here, here and here. I will try to write down it in red color. Z bar S1 star and Z bar S2 star are here. P S1 star, P S2 star, or say P prime S1 star, P prime S2 star, and P, all are given here. What you have to do, you simply have to substitute all these expressions over here, and you have to simplify it. And whatever you get, that is going to give you the form of the Murthy's unordered estimator. Do you think that is it very difficult? No. Yes, the terms are little bit, the terms may become little bit lengthy, but lengthy does not mean complicated. So you can see here that I have just substituted these values, nothing more than that. This is your here Z bar S1 star, this is your here Z bar S2 star. These are the probabilities which you have written here, and I simply have to just simplify it. Do you think that is it very difficult? Not at all. Right. So I simply try to simplify it here. First of all, this 1 upon this value will get simplified, and we will have this expression. And if you try to just combine here all the expression related to yi upon pi, you can see yi upon pi is here, yi upon pi is here, yj upon pj is here, yj upon pj is here. So you simply try to combine them, and you will get here this expression, and if you simply try to simplify it, this will come out to be like this one. Z bar u will become 1 minus pj yi upon pi plus 1 minus pi times yj upon pj divided by capital N 2 minus pi minus pj. So you see, after solving it, it is coming out to be in a very simple and nice form. So this is your Murthy's estimator, which is corresponding to the two ordered estimator which are obtained using the methodology of Desh-Raj estimator. So this is now estimator, and now we will try to check its unbiasedness and variability. Right. So now we know when I am trying to take here yi, this yi is going to take any value of this y1, y2, yn, and the corresponding probability is going to be small pi, which can take any value capital P1, capital P2, capital Pn respectively. Right. And similarly here yj and pj also, they can take any of the value of y1, y2, yn and p1, p2, pn, except the value which has already been taken in the taken by yi and pi. Right. So yj and pj, which are occurring at the second row, they can take all possible values except the values which have already occurred in the first row, and the same thing will happen to yj and yi. Right. Now, in case if I try to take the expectation of z bar u, you can see expressions may be a little bit lengthy, but they are not complicated. So I simply try to take the probability and try to take this expectation using the basic fundamental. After that, what I am doing here, you can see here that here we have a symbol I less than j. The summation is going from I less than j, and I want to convert it into I not equal to j. Then the algebra will become simpler for us. So I try to do here one thing, that I try to multiply and divide by the factor 2. So now once I am trying to combine this twice and summation I less than j, this will be converted into I not equal to j, and this 1 upon 2n will continue here. So that is the first step. Second step is this, I have done very simple algebra here, that this is continuing, and now I simply try to simplify it, and I get in, if I try to simplify it here, I get this thing. So up to now I have done not much difficult algebra here, this is very simple. You simply have to just come from one step to this step, and if I start doing it right here, possibly you will also get bored. That right. So now after this, there is an important thing which I am going to do. So now we have obtained our this expression like this. Now I will try to play with these two terms over here. We have a result which says that I not equal to j going from 1 to capital and aibj. Aibj are some known constants. This can be written as summation I goes from 1 to capital and ai, and this bj can be replaced by summation j goes from 1 to n bj minus bi. And you can see this is a very simple thing, right? It means you are simply trying to replace bj by means all the sum minus a particular value. Okay. So now I try to use this thing, and here if which I am marking here in say red color, this pj and here pi, I am trying to use this result, and this will become here yi upon 1 minus pi, and this it will become here j goes from 1 to capital N pj minus pi, and the same thing is here for the second probability. Now if you try to see what is the advantage, the first advantage of changing the summation I less than j to I not equal to j was that I can use this result. And once I am using this result, then you can look at this factor. Summation pj is going to be 1 and summation I pi is going to be 1. So now this factor becomes here 1 minus pi and 1 minus pj, and 1 minus pi and pj, they are going to be cancelled like here, and then you are getting here 2 times the y total, right. So this becomes here capital Y bar plus capital Y bar divided by 2, which is here capital Y bar. So one can see here very clearly that this is an unbiased estimator, and that is what we want, right. So this Murthy's unordered estimator comes out to be just like an ordered estimator. And you see why you have done this algebra. You can directly obtain it from the theorem also, because you already had proved that Desharaj estimator is an unbiased estimator. So if Desharaj estimator is unbiased and you have constructed the estimator using the methodology of that theorem, so the resulting estimator will also be an unbiased estimator. But anyway, I wanted to show you this methodology, that is why I have done it here. Now, finding out the variance of the z bar u is a little bit complicated, so I am going to give you only here the expression. And now my question is that what about this variance, how will you say that whether this variance is going to be smaller than the variance of the ordered estimators. Now, sometimes students start thinking that they have to take the difference of variance of z bar u with respect to the variance of Desharaj estimator, but that is not possible to do, because it will come out to be quite complicated, and particularly when you already have established with this theorem that if you try to follow the methodology proposed in the theorem and you try to construct an unordered estimator z bar u using the ordered estimator, then the variance of the unordered estimator will always be less than the variance of any of the ordered estimators. So using the result of that theorem, I can write down here directly that the variance of Murthy's estimator will always be less than the variance of z bar S1 star or z bar S2 star, which are based on the Desharaj estimator. So now you can see here, now you have constructed an estimator which has got a smaller variance than even the ordered estimator. So you should now be happy. Okay, so now I am just giving you here the expression that how to estimate the variance of this z bar u. So this estimator of variance of z bar u is given by this expression. I am skipping the proof here, right, but if you wish you can use it in real life application, and this is not difficult to compute. You can see here that pi is known to you, pj is known to you. So and right, so and this capital N is the population size, that is also known to you, yi and yj are known to you. So it is not difficult to compute it in practice. Okay, so now we come on one more topic, and we have seen that when we are trying to use this unordered estimator, there is a problem. Means I had just shown you this variance here, but I had not given you here the proof of this estimator, this variance of this estimator. because that becomes too complicated to handle. Right. So, in order to solve this problem, people started thinking that how to handle it. And particularly when you are trying to draw a sample of size capital N. Now you see, if I ask you to consider the Murthy's estimator for the sample of size small n, I mean theoretically there is no problem, but computationally you can see that is going to be a challenging job. So that is why people started looking for some good solution, and then this Horvitz-Thompson came forward and they proposed a Horvitz-Thompson estimator for the population mean, where they could handle these types of issues, because they realized that these unordered estimates, although they are nice, but they have a limited applicability, because they are not so simple to obtain, because when you are trying to go for any, say, higher order discharge estimator, then you have to construct all such estimators, and then you have to find out such an expression. So, which will really become difficult to handle, and the expressions will become complicated and their variances become unmanageable. Even if the sample size is not so large, but it is just moderately large. So, then Horvitz-Thompson estimator came to help us, right, and it is simpler than other estimators. So, now in order to understand this estimator, let us first assume that we have a population of size capital N as usual, and we have these units y1, y2, yn in the population, and from there we are trying to draw here a sample of size small n by varying probability scheme WOR. And for that, the advantage is that here I can use any arbitrary probability of selection at each draw. What does this mean? Let us try to understand. Because you have seen that in the case of without replacement, prior to draw any of the unit except the first one, you have to redefine or you have to redistribute the entire probabilities, and hence you have to define a new probability distribution prior to each succeeding draw, right. And then you have seen that earlier we had seen that the probability of the first unit, that was fixed, but after that you have to compute them again and again. So, thus prior to each succeeding draw, there is a defined new probability distribution for the units available at that draw, and the probability distribution at each draw may or may not depend upon the initial probability at the first draw. This is what was considered in this Horvath-Thompson setup, Horvath-Thompson estimator of population mean. So, for that what we try to do? We try to define a random variable here alpha I, and we try to associate an alpha I with each and every unit in the population. I goes from 1 to capital N, and we define that alpha I is going to take the value 1 if capital Y is included in the sample small s of size n and 0 otherwise. Now, once you try to do here, then I can define a new random variable. Now, you see how to define this new random variable. That is the same thing what you have done in the case of when you define the zi's, but now there is a small change. What is that small change? I will try to show you. So, first I try to say here, let zi be equal to n times small yi divided by capital N times expected value of alpha I, and this I am going to define for all the units in the population, and we are assuming that expected value of alpha I is greater than 0. And if you try to see here, what is this expected value of alpha I? This alpha I takes value here 1 and 0, you can see here. So, now this becomes here 1 into probability that yi belong to S and into 0 into probability that yi does not belong to the sample S. So, this probability you have assumed to be pi I. So, this is here simply here pi I. Pi I is the initial probability of including the ith unit in the sample. This is the pi I is the probability of including the unit I in the sample, and this is called as inclusion probability. Probability is always greater than 0. So, this thing actually becomes here n times yi divided by n times pi I. right. So there is no problem in assuming this that expected value of alpha is positive, right. And based on that, the Horvitz-Thompson estimator for the population mean is defined for the sample small y1, y2, yn as simply the arithmetic mean of small zi's like this, and we try to define here as a z bar n, or we try to write here y bar hat st, means Horvitz-Thompson. And in case if you try to write down this thing in a simpler way, this summation of n z I can be written as a summation I goes from 1 to capital N alpha I z I. Why? Because alpha I will take value 1 with all those values which are available in the sample, and it will take value 0 with all other values which are not in the sample. So their sum will become same as this summation I goes from 1 to n z I. So this is the way in which we can express the Horvitz-Thompson estimator as 1 upon small n I goes from 1 to capital N alpha I z I, where alpha I is the inclusion probability. Inclusion probability of what? The probability of including the unit I in the sample, and this you will see that this is going to help us a lot. And handling Horvitz-Thompson estimator from the mathematical point of view, from the algebra point of view, will be simpler, and we can do it for a sample of size small n. This is what we have done here. So now we stop in this lecture, and now you have seen that we have developed an unordered estimator based on the ordered estimators. And now we also have defined the Horvitz-Thompson estimator, which is trying to overcome some of the issues which were defined in the Murthy's estimator. So on the next turn, I will try to continue with this Horvitz-Thompson estimator, and I will try to find out the statistical properties of this estimator. But as I said, that whatever we have done in this lecture, I request you to do the same algebra yourself. That will give you a lot of confidence, and you will understand that why are we trying to reach from step 1 to step 2 in a particular way. So you try to practice, and I will see you in the next lecture. Till then, goodbye.